Nicola and Andrew.
They'll have 2 minutes.
Yeah.
It's a good talk session, isn't it? Two of them were ones that we wanted to go to.
Okay. Well, my duty finishes today, which is okay.
Oh, that's good.
Yeah, no, I mean, I cannot chair my own lecture. Can Oh, Nicola is chairing, and we don't have Granny, Dennis Morris.
Sitting here by the window. Oh, yeah. Yeah, it's hot today. Yeah.
Yeah.
It is.
It's nice photo.
Yeah, it is. It is a very nice photo.
There's other places near there, Chichester.
Yeah, that was the last time I saw Mike, unfortunately.
There's another place. There's a big
I always think it's more difficult for people to learn behind than the one who's gone.
I agree.
Yeah.
Yeah.
I mean,
Well,
yeah.
If we don't with somebody, what is it worse?
Exactly.
SS code.
Yes.
Yeah. Yeah, and Andrew will come. I mean, he's supervising the removal of stuff. So
Yeah.
but he will come.
Yeah.
So whenever you are ready, Ulrik.
Thank you.
Yeah.
Yeah.
The
recording is on. Yeah, the recording is on. Yeah.
Okay, can I introduce Ulrik Vendelbo?
Yeah.
Who is the son-in-law of Mike Manthey. And I don't want to talk too much. I leave it to Ulrik to tell us a little bit about Mike, but also what are his plans for the future research. Thank you.
Thank you. So welcome to this talk about Mike and his research and the road ahead. I'll just. Is it error to continue? It's always awkward.
Try the mouse.
Yeah. Something happens. Okay. So who were Mike Manthey actually?
Ice cream break.
Okay. That's ice cream break. Yeah.
Thing you might have done.
Oh yeah, exactly. He would like to make fun. That's for sure. But yeah, actually, Mike, he was like educated in mathematics and especially in computer science. And he also stayed in New Mexico in the computer science departments for some years before he actually went to Denmark, to the University of Aalborg. And in the 90s, he was actually a tenure associate professor there in Aalborg. And he did a lot of his, I believe, main discoveries, main research in that area. And then actually, Mike, he was a very keen musician. He liked to play music and things. So he actually invented the world's first like purely digital real-time sound synthesizer around that time. So that was like quite a huge thing compared to what they have before in music. So that's one of the things he did. Then he actually retired in '98, decided to move to the mountains in Colorado, found a nice place, He built a house there, and then the reason for that was like twofold. One was to pursue like full-time research, but also to do meditation. So he was very much into like the research and meditation and the inner workings. Then he had begun. Then he was ANPA member and president for many years as well. And then he also in 89 invented like a coin demonstration, and that's a way he used to like demonstrate how to move out of like the limitations in normal computing to something else. Then he actually hold several patents. So he has patented a lot of his ideas actually over the year. And then, of course, he's a proud father to his only daughter, Solveig, my wife. I'll just see what I can do. If the mouse will find out. Okay, now it works. So, yeah. So who am I actually? Yeah, I'm like the bloke who met his daughter back in 2008. And then I, of course, got to know Mike a little bit over the years. I have always like been interested in computers since a kid. It's always been fun and interesting for me to like what you can do with those boxes in the early days. So I actually started computer science at the University of Aarhus, but I got an opportunity to join a business opportunity to become a partner in a business. So that time I decided, okay, I can always study again. And then for many years, I was like out in the business world. Then I actually, after now, having family, having 3 girls, I have been taking up programming again. A couple of years ago, I started to like talk more deeply with Mike about it and try to help him with some of the coding. And that resulted in that now I'm actually quite deep into like implementing Mike's space-like computing. Yes, this is a picture from the last visit at Mike's place in the mountains. He actually built this house, a bale straw house in the mountains, and with the idea of having like a garden inside. So like a very big like jungle garden inside in the house. So that was like where Mike he lived for a very long time. Quite a special place, a nice place, very quiet. So you could really like feel nature and things like that. And in that place, actually outside, Mike had this bench under 2 trees outside, and that was where he was doing his sitting, his meditation, and his thinking. And actually last summer, me and the girls stayed 5 weeks at his place, had a very good time together. And that was one of my girls like just filming me and Mike sitting and talking. Then if we look into what this neural network things we are doing today is, it's not something new. It's something from like in the middle of the 50s from Dartmouth or something. But from the beginning, I was talking with Mike. He always like emphasized that in his belief, like neural network was basically flawed. There's something wrong with it, basically. So that's why he was like looking into what can we do instead of just doing like what everybody else is doing, neural networks today. And why is something flawed, or what is actually the first way you will notice something is flawed? That could be that, like the case with OpenAI, they start hiring a lot of lawyers. Then maybe you should be a little bit aware that maybe there's something not completely just working by itself. So actually, yeah, a lot of lawyers is apparently being hired and paid to help OpenAI figuring out the problems they seem to have in some areas with this new technology, especially the large language models they are introducing to the world and a lot of people and companies are using today. So that you should be a little bit skeptical. Something is maybe not perfect. A different thing I find quite interesting is a recent paper actually from Stanford and Rice. That is that some scientists, they have tried to investigate that if you have a neural network, especially if you have these long, big language models, then the way it works today, that is like if you have this ChatGPT and thing, it's basically trained more or less on all the information we have today on the internet. So you're taking a network and you're training and you're training and you're training with all the knowledge we humans have created out on the internet. And that's what we're using today, and that apparently it works for many things. Sometimes it's a little bit biased and whatever. But then we are also today using those large language models to produce new contents. So they are producing, papers for us, and they are producing images and things like that. And that goes out on the internet. And then we have new models that's trained on something that's partly made by humans, but also made by machine. And they actually investigated, and it's quite interesting paper, this one. What happens when the amount of information you're training on starts to become more and more from other machines? So when you're training machines on the output from other machines, what happens? It seems like in some cases, very few repetitions, like 5 times, then what you're putting in and training, it gives something totally crazy. So the more you're training a network, a neural network, a big neural network with content that's generated from other intelligent machines, something strange happens. It actually, it breaks down, basically. So the more the machines are consuming things machines have made, the worse it gets.
It's like machine incest.
Yeah, you can say inbred. They are comparing it to mad cow disease, basically. So now we have lawyers, and we have, in some cases, neural networks, and especially the big models. We should be a little bit suspicious that maybe not everything is good.
Several years ago, it was rubbish in, rubbish out.
Yes. So garbage in, garbage out, basically. That means that actually very early on in the 80s, Mikey realized that something different was needed. We should think in a different way when we are thinking intelligent machines. And that's what he had been thinking about for a long time. Here I'm trying to compare what we are doing today with neural networks and Mike's idea about what we could do. I want to emphasize that just because this is red and this is blue, it's not like this is totally bad and this is totally good. In my opinion, what we are doing with neural networks today, it has a place in the world, but it definitely don't have a place in the big language models and things like that. So in my opinion, if you use a smaller neural network for some simple tasks, very constrained tasks, it's a nice tool and it works and it's not too difficult to train and things like that. But if you try to scale it up and make it like thinking like a human or whatever, we're going into problems. But basically, what we're doing today, that is, we are taking a network of, and then we are throwing in informations and we are adjusting some weights. That's what we're doing today. And in my opinion, it's a kind of an advanced comparing machine or a copy machine. So that's what we have today. What Mikey was thinking about, that is a way that we can have a machine that can actually generate information more or less by itself, and where it don't need to be trained a lot all the time. So that's like a huge distinction. So it's more like, how can we make a machine that can act like a child being born, who knows nothing, starts interacting with the world, and then it learns within that interaction and grows up and it becomes something. That's more the thinking. If we do that, then there are some nice, interesting things. And that is, today we have difficulties, and that's probably why they lie us. Nobody can tell how the decisions is made in a neural network today. It's like a black box. You put something in and it says, oh yeah, it's a cat or it's a dog. But you cannot ask it, why is it a cat? You can't see it. Even the programmers can't go in and find out. So we have these issues with biases, especially when you start to using this as profiling people, maybe being bad guys or less bad guys or good guys, and even judges are sometimes getting help from machines and black bias and different things. So a different way, that is, Mike, he was thinking about generating information by co-occurrences of things. And if we do that, then we actually have a way where we can go back. So that means that it supports transparency. So we can actually go back in the system and see how it reached this conclusion. Neural networks needs a lot of data to train. What Mike was thinking was more like a child growing up, few repetitions will very fast learn something. Neural networks, it's only one way. You're feeding in information, goes to a network, and a result coming out. In Mike's way of thinking, it's more like wave-like. Something goes in and comes down. I'll get back to that. What we have today is what I'll say is like narrow artificial intelligence. It's good for very small tasks, but you cannot, as I know it, scale it up and make it like a general artificial entity. What Mike is suggesting is actually something that would be able to learn everything, whatever it's trained on. So it'd be more general entity. And then neural networks, it has like a fixed amount of input layer. If you train a network, then you cannot say, now I'll want 500 extra sensors and throw in. Then you have to start over and train again. In Mike's system, it's more flexible. You can adjust the amount of input to the system and it will react to it. And so basically, with Mike's work, it's more like time-like what we are doing today. And Mike's suggestion is that we should move to something that's more space-like. So the big question is, if we should do that and make it work, how do we like generate information instead of consuming it? Because if we are thinking time-like as we're doing today, then in computing, we have one step, next step, and third step. And that means like if we have 3 + 4 equals 7, then at the moment we have the result 7. The computer cannot tell how we reached that result. It just did something. So we need to move to a place where we can actually like tell how we got some result and where it came from. And that was something Mikey was thinking a lot about. And then actually back in the 80s, he came up with an idea. He's called the coin demonstration. He has probably been showing it to people many times, but I will try and go through it again. So basically what it says, that is that I think I have 2 coins. I actually think it's Mike's coins just to make it fun. But that means like if I take my hands behind and I put one hand and show you one coin, then I close it and remove it again. And then a moment later, I'll put forward a hand and show you one coin. Then I'll close it again. And then I will ask you, how many coins do I have? What will you suggest will be the answer?
At least one.
So at least one, yes. So could we agree that it could be like one or more than one? Yeah. So I have one or more than one, right? Then the issue is, how do we decide this? So what happens when you can answer this question, how many coins I have? So one or more than one, that's the two possibilities. But you need to receive one bit of information before you can decide if it's one or more than one. So now I'm actually showing you that I have 2 coins now in my hands. So now you can give me an answer. You can actually tell me how many coins, and you can say more than one. But how does that happen? The interesting part, Mike, he was very interested in, that's actually like, where did that information came from?
From behind your back.
Yeah, from behind my back. Yeah, we could say that. But how could you actually now answer the question? And Mike, he believed that it's the simultaneous presence of the 2 coins, that they're now present, the 2 coins at the same time. That gives you one bit of information. So that means that just the co-occurrence of the 2 coins have given you one bit of information. And that's quite interesting when you start like thinking about it. Because that means actually that if you're thinking in co-occurrences and there's information in a co-occurrence, then you're actually in a world you cannot reach sequentially. And that means when you're talking computers, now we're outside of the limitation of Turing's world, Turing's box, whatever you call it. So just remember there's information in a co-occurrence. And that's the same again. The co-occurrence gives us information. So just the simultaneous presence of something, the gift is actually making information. So we're a long way from traditional Boolean algebra in this area. Then I would like to try to explain a little bit more, because what Mike he has been doing, he has like built all this together. He tried to do some mathematics and how we could do some thoughts about implementing it. And he's calling it all like space-like computing. And he has patented that part as well. But that means that now we can actually do something else compared to a neural network. If we have 2 places, A and B, 2 platforms, and we have a sensor A with a plus and minus, and that'll be like empty platform or something on the platform, right? We have the same over here. So we have 2 platforms, we have 2 sensors. Then we can actually look for a co-occurrence. So if we have a system that's looking for A plus and B minus, that means that A is filled and B is empty. When that happens, we actually receive a bit of information. And what we receive, or we can at least build with computers, that is, we can say that this co-occurrence of these 2 states, that's an impulse. That could be an impulse to empty A and fill B. So we have a co-occurrency, and then in Mike's world, that co-occurrency is an impulse, and that impulse is actually like bubbling up in the hierarchy. And when it reaches the top, it's changed to a goal, and then it triples down. And on the way down, it looks for a plan to do this in the system. This is a very simple example. Then it becomes, or it touches an effector, and this effector is basically changing these two at the same time. So it empties A and fills B. And now we have moved the box from A to B. The very interesting part, in my opinion, is, so if we're like looking to what happened, that is, what did we do? We have a system with two sensors. And in these two sensors, like a confined small world, as soon as we sense this co-occurrency, A filled, B empty, it automatically gives us some information. We are creating information we can use to look for plans to move A from B. And that's critical, because if we're thinking that way, then just by having a lot of sensing capabilities, just like our brain have, then our brain could actually internally, or the system will internally build something just based on the sensory input, and it will decide what to do. So we don't need to train the system like neural networks. Of course, it won't work just with two sensors like this, but you can combine in each levels. You can have more than one co-occurrency happen, and you can have meta sensors detecting co-occurrencies of co-occurrencies, and so on. And that's very interesting, because then we actually can say in a system like that, if we build it, then learning is actually patterns of synchronization. So the patterns that's built depending on the co-occurrences we are receiving and detecting from the sensoring interface. So I find that very interesting. But one thing is finding something interesting. A different thing is, of course, like, will it work? Were Mike actually on the right track? Is it worth to do something about this? Mike, he left a paper that's not published, and it will come here in ANPA latest next year, where he is like looking a lot into a mathematical model about explaining all this, what's happening in this hierarchy of co-occurrences and co-exclusions and so on. So he used a lot of time to make a huge mathematical explanation and reasoning about that. That's not my strong side. So I hope you will help and see what works and what won't work. In this mathematical model, he actually like found these following forms. So he was, besides just thinking about how to build intelligent machine, my impression was he was thinking a lot about how the universe works, quantum mechanics, all the things he could actually like research into. So I find that interesting, but I can't validate his thinking. I can't follow it. So I don't know if there's something there or not that's really interesting, but I hope that you will help with that. So why I believe that Mike was actually on the right track. What we see today in neuroscience, or actually for many years, that's the discovery that the cortex of the brain is built of like similar units, and they're calling them like cortical columns. So it seems like the brain is like one column, and then 150,000 of them that builds our whole cortex, like the outer part of our brain, where we believe everything is happening. So that's like from neuroscience today. Then it's believed that one causal column like this, since it's replicable, nature have it with replicating stuff, that it probably is like doing the same thing. So maybe there's one kind of universal algorithm or some basic algorithm, if you're looking with computing, that's happening inside one cortical column. So that could be interesting to investigate. There is a guy here. He actually made the Palm Pilot, I think, to begin with, the small, very first nice handheld computer. He has been very interested in how the brain functions, and he has started the Redwood Neuroscience Institute, where they have a lot of researchers and thinkers about how is the brain working, and they're trying to like prove what they can prove about it. And they came up with the idea that the brain actually builds reference frames. And that means like the brain is inside our skull. It's not connected to the world, but it's connected. It can see and it can hear and do stuff. But how does our brain know that if I'm touching my hand, or if this is my phone, where my phone are, so I can actually grab it and move it around? That's like, they were thinking a lot about that, and they came up with the concept of reference frames. So somehow to build like reference frames or maps and things, so the brain understand, okay, there's my cup, there's my phone, if I'm going in this direction, or so the things are shifting. So the brain, due to their research, is updating reference frames all the times. And I have like a little bit feeling that reference frames, it looks quite like if you have patterns of synchronization, if you build this co-exclusion and co-occurrences hierarchy Mike is talking about. So some patterns mimicking the world, and maybe that's how it works in the brain. Then I was also thinking, yeah, but maybe there's more just to it. And so I also, sorry? Okay. I also think that we can just think of nature. It seems to me, at least, that nature is concurrent. And then there is new research that suggests that our brain uses quantum computation. And actually today, John here actually also suggested that that's true. So I'll just take that as evidence. So let's say the brain is using quantum, right? Then if you have a child and you show them cats and dogs, they would quite fast learn what is a cat and what is a dog. You don't need to show them 10,000 pictures just to have a chance of guessing a little bit correctly. And if you think about it also, I think the brain is much more energy efficient compared to the computing systems we're building today. So that also gives my impression that maybe there's something that's interesting to work with. So if we buy into that, yeah, it would be interesting to do what Mikey was thinking. That could probably be an interesting way to do something. Then how do we build it? We need three things. We need some programming language or paradigm that we can start building it with. We need to think about how can we implement this, like two things happens at the same time, this currency or co-exclusion. And on top of that, we need to think about how can we like make a forever running piracy that's continuously reacting to the world. So that's like the main challenges. The first one, what programming language or paradigm? I have chosen the language called Erlang. And it's because that Erlang actually reflects how things happen in the real world. It has a built-in support for massive concurrency. It's built of a lot of small processes, individual small processes, or thread, if you like, that concurrently is working. And they are interacting with each other by message parsing in this programming language. It's actually like used in telecoms, banking, and also like WhatsApp. So when people are using WhatsApp, since you have so many people communicating and things at the same time, things happening at the same time, then Erlang is very good for it. It's a functional programming language, and it has built-in the possibility to forever running loops. That's just a basic property of this language.
Can I ask people to mute themselves before discussion, because we are getting some people.
You need to mute dot. So then the second thing is that how do we actually like represent and detect this co-occurrency thing if it's difficult to do in traditional computing memory? Yeah, it's one that's talking, but yeah. So basically what we need, that's a kind of information sharing system where things can happen concurrently.
For a fire complex.
Can you please mute yourself for the next 5 minutes?
Yep. So the concept, Doc, can you hear me?
Yes.
Yes.
Yeah, yes, I can hear you.
Okay, perfect. Can you please mute yourself and then after the presentation ask questions? Thank you. So we need something different that the computing memory have today. Luckily, somebody already invented it. Very nice, good idea. Came out of MIT in the 80s. And it's called a tuple space. So somebody already invented it, but it haven't really got mainstream in computing. What's interesting with this tuple space is that when you're looking for something, you're addressing it associative instead of just by address to receive something. Then this tuple space, it has a range of operations. So the original implementation, it has like out, in, read, and some predicate of those and eval. That can do something. We'll come back to it in a moment. But Mike's idea, what they always was playing around, but have trouble implementing in C back in the 90s, that was to add some extra functionality to this tuple space concept already invented. And that was like the detection for co-occurrences and co-exclusions and so on. So what is a tuple space if we should try and explain it quite easily? It's a blackboard metaphor. So it's basically what we see around here. That's different processes, individual processes, and that could be in Erlang, not knowing each other, right? If they want to communicate things, then we have one program over here. It reads its program and then have an instruction saying, oh, out. That means throw out this tuple into tuple space. So this process, it builds this. So now in tuple space, there's invoice 2,500 Great British pound, right? Tuple. Okay, and it succeeded. Then we can have over here, I will take, yeah, in the tuple space, there can be already a lot of tuples. So everybody can come and put something on the blackboard, or they can take something from the blackboard. They don't need to know each other. They don't need to be present at the same times and things like that. So that means if this one is coming in its code and it goes to an instruction that says, oh, is there a co-occurrency of two tuples, tuple A and tuple B in tuple space? It looks in tuple space and yes, there were two. And then it's allowed to continue in its code, right? Then there is a process down here. It's looking, it's read. So it's looking in tuple space for a goat. the value goat. But there's no goats in tuple space. So what happens is actually now it's blocked. So this process in its computer instructions, it's blocked. It's not allowed to continue doing whatever it's doing before there shows up a goat out in tuple space. Maybe never, we don't know. So it's blocked. And that's the same down here. This one, the concurrency, the interesting part is it's not just 2 tuples. It could be any amount or number of tuples it's looking for. So it could be 1,000 different tuples. When all is present at the same time, it's allowed to continue. But since we are missing a C, there's no C in tuple space, this one is blocked as well. This one, it asks tuple space like in. It's looking in tuple space for something. It looks for an invoice, and it looks for Great British Pound, and then a question mark. And that's the associative search that's coming in. That means, okay, look in tuple space, find a tuple of 3 elements, where it's first is invoice, the last is Great British Pound, and we don't care what the middle is. And it looks in, oh, there are 2 of those, but it takes just 1 of them, and deletes it in tuple space and give it to this process, and it continues doing stuff. So that's the basic mechanism of a tuple space. So what is it good for? Basically, it solves a lot of problems that people are doing in very hard ways today, actually, in computing, instead of doing it simple and easy. You can easily coordinate parallel computing, like master worker tasks. You can do process coordination between processes. You can do synchronization through the tuple space. You could use it as distributed data structure. You can build your arrays. You can build lists out there. You can build whole mathematical structures. You decide how they are, throw them out in tuple space and react on it. It can be used as a database system if you want, basically, and a lot more depending on how you're implementing this tuple space concept. So that's a very interesting thing. And I've been implementing quite a lot of this in code. This is in Erlang. Small example. I'm now compiling the program in Erlang. That's what happens. Then I start. I'm calling it an info-register space instead of a tuple space. That space is now created. Now I'm starting a test process, a separate test process, which job is just to populate tuple space with, in this case, 100,000 random tuples just to fill something in. So now I'm filling in 100,000 tuples in this tuple space, and it takes half a second for 100,000, but just boom. Now I'm starting a process, one single process with a job asking for when is A and B present in tuple space, like the co-occurrency of A and B. I made 10 of those. So now we have 10 processes all around the tuple space, independently, concurrently doing stuff. And now I throw out an A, a tuple A to tuple space. And I also throw out a tuple B to tuple space. And in that instant moment, all those processes actually notified at the same time in the tuple space, and they can continue doing whatever they're supposed to do. So what takes longest time is actually to write this text to this terminal. So that's some of the things the tuple space can do. So it ends actually up as like a kind of coordinating language for computers. You can use a tuple space for, and that's an important part. Then the next part is, how do we like build this forever running hierarchy to connect to an array of sensors outside to the world and to react, like detect co-occurrencies, and by that detection generate information and acting on that information. That's very interesting. Yeah. 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 And that is like One way is, of course, focus on looking into the details of this algebraic model Mike is like suggesting for this whole things. I really much would like people to look into that and let me know that are there some issues there? What can we do there? Are there something where this is definitely not possible in a mathematical sense or physical sense, right? Because then maybe I could adjust what I do in code. So that would be really interesting if people do that. Then this tuple space I just showed you, it's running in RAM on computer, so it's running very fast. It needs to be fast. If it's not fast, then you'll end up with a very slow computer and it doesn't matter. And then we use this Erlang language because the built-in process system and the forever running loops. And then we can build actually what Mikey has patented. So what is the road ahead? I have already implemented most of this extended tuple space concept in Erlang, which I call an inforista space. I like coffee and it's something with information. So instead of barista, it became inforista, right? So then when that part is finished, we need to build and test this space like computing hierarchy. That's actually only not so many processes running concurrently on top of this, and then we can start playing around with it. Then the obvious things that's always very difficult and easy to say that it's introduce the system to the world, use the system to do good stuff, fight against misuse of AI generally. Space-like computing is patented, so of course try to protect that way, and then even try to use a good AI to fight off bad AI, because that's probably what we need in the future. We can see it already today. Some people are actually programming good neural networks to detect when neural networks are making like fake images and things like that. So there is like a race going on. Then this is not public yet, but it's a closed website, but that's like the main idea, that is to work on development, this new kind of AI, introduce that to the world and use it to actually do some good stuff. And that means explicitly not do bad things like war, advertising, surveillance, gambling, and whatever. So keep in mind to do something good, even though it'll be very fast and much easier to earn money that way. But we don't have to, we have to avoid that. This is some of the documentation for this API, this inforista space I'm building with a lot of functionality in. So I'm working on this. So I'm in this place where when I have the time, I work on my computer and let's see if it works or not. I'm sure all this I can make work. I have all the technical things is already thought out and it works. Maybe I'll have some challenges understanding the whole hierarchy and the running concept in the mathematic parts. Luckily, Mike did quite a lot of pseudocode how it should work. So I think what all the things I have learned from Mike, his last papers, but actually also his papers from the 90s, I have all the information to actually go build a new kind of artificial intelligence, real general intelligence that can learn anything and grows up like a kid. But it's like slow evolving, just like a child. You have to learn it and interact. But it will be able to do anything. And I think that's like the holy grail in artificial intelligence, if you can do that. But I think it's possible. With that, I will actually, while reading all the things from Mike, I will end this presentation with a word from Mike from 1978. I'll just try and see if I can move this one a little bit. Yeah. What Mike says, and I think these words says a lot about Mike, who he was and how he was thinking. But there's also some wisdom in it, if you like. So Mike says that the word purpose implies the existence of some particular outcome, an ultimate result, and as such is implicitly sequential notation. Systems like nature are not sequential, do not explicitly produce any particular outcome, and hence have no ultimate purpose. The burden on us as spiritual beings is to find it within ourselves and not fob off the responsibility on a system which will destroy us if we fail. So that's the last word from Mike. Thank you.
Thank you.
Yeah.
Can I ask Mike formally, because I saw him raising
Yeah.
hand. Mike, do you still want to ask something or comment?
Yes. I work very closely with Mike, and one day I was sitting next to him when the guy who wrote his obituary, which is published, David McGovern, came up with a very simple idea, which is roughly the same as the 2 coins. If John Rowlandson is in the audience, I ask him to take a piece of paper, which is roughly square, fold it in half twice, and then tear the inner corner. And out of the piece of the original piece of paper, if he's done it roughly, there's like a diamond. And this is not the opposite of the original paper. It's Mike's way of saying there's one bit of difference in a physical reality situation. I was very impressed with that, and I kept a piece of paper with the little piece ripped out in my wallet for 10 or 15 years, and whenever I took it out, I remembered Mike Manthey.
Yeah,
Thank you.
Okay. Any questions from the audience here? I have to say that we are melting.
Yeah, we're melting. It's very hot inside. That's right. Yeah.
So, okay.
Yeah.
You use the word tuple.
Yeah.
Is that linked to Cartesian products?
No, it's in my world, it's just some piece of data. You decide whatever it is.
Okay.
So the tuple, it's just like, it's not a list where you can have unlimited element. It's a fixed length tuple. So you decide when you're making it if it should contain 3 elements or 100 elements. Or,
So it's a flexible structure.
yeah, it's a structure where you decide if it should contain 3 or 100, right, to begin with. And it can include in the places in the tuple, you can throw in like lists, strings, integers, whatever. So you can like store everything in tuples, and that's why it's clever that you can use it to a different way of doing storage in a computer.
Yeah.
Okay.
Yeah, I love this. When we talked about it over breakfast at some stage, because you're Danish, I didn't hear tuple, I heard topple.
Yeah.
And I thought that was a lovely thing because it's an idea of a space that things can fall into,
Yeah,
or fall out of, and
Yeah.
can produce things which then,
Yeah.
which then initiate a stream of events that
Yeah.
come from something that's looking at,
Yeah.
like a picture of the, like a copy of something like the real world that we're looking at the moment. We have something that has a set of things in that react to. You know, if a rabbit comes in, you do something. Things happen, and the kind of structure you
Yeah.
have there looks to me like a much closer thing to reality than the way these things are normally done.
Yeah.
Because you can have a very large number of things that are
Yeah.
looking into this space, and the space can have a very large number of different kinds of objects which come into it.
Yeah. Yeah.
Which act on it. It's very beautiful.
Yeah.
I can see that Doug has raised hand.
Yes. What do you say, Doc?
Hey, yeah, I have a question.
Yeah.
I think you and I have talked about this, Ulrik, that, the tuple space, you're still doing a matching, right? You're doing a search in the tuple space for things.
Yes, that's correct.
in the match. And can you care to comment about whether or not that scales?
It scales. Let's say the search in tuple space happens in constant time or near constant time, no matter the amount. So even like 100 millions of tuples, it's nearly instant search.
Or is this because it's using some kind of hashing algorithm or something?
I'll say as much as I built the basic structure with key value tables. So that's as much as I would like to say right now.
Okay.
But yeah, I have like figured a way around doing extremely fast search, like associative search in the top space, and that's
Okay.
like a very, very important thing, because
Yeah, because
if
the
you are
space
very
goes
fast
up.
at throwing things out and things, but if it takes forever, you know, to retrieve things and find things and do stuff, then it will get slow. But
Yeah.
Erlang has a concept of Erlang term storage. It's a kind of table you can build in memory in RAM in Erlang, and it is actually built so it is accessibly concurrently from all the different processes running in Erlang. So it's a very interesting data structure you can work with. So you can, in many situations, you can actually scale it up easily. Yeah.
Yeah. Okay. So, I mean, because I worked on neural computing stuff too, and we were doing associative style memory. I mean, essentially Hawking is working on Canerva memories. And Canerva memories are content addressable memory. And the way you find something that's near it is that you find essentially things that are near it in the space. But in order to do that, you have to actually have a high dimensional version of radar that doesn't scale with this with an infinite number of dimensions. So and so even though it seems like a nice idea mathematically, its implementation does not scale. I mean, you can put a lot of concurrency on it, but somehow the quote brain / mind scales where, you know, where these other systems don't necessarily scale. So so
I totally agree, and I think it's a very interesting like engineering problem.
Yeah, it is. Yeah.
Actually, I did a little bit math this morning back at home, just because if we are looking into the knowledge of actually a human brain, how big it is and connections and things like that.
Yeah.
People says that it's about 86 million neurons in the brain. I was trying to calculate back, okay, how much memory RAM do we actually need to have in this Erlang system to do that? And it turned out if you take around 400 computers, each having 100 gigabyte of RAM, then you can actually simulate, then you can handle the amount of neurons you have in the brain in Erlang. And luckily, Erlang is actually made so it works distributed, that's built in the distribution. So you can just start up an Erlang node on each of the 400 computers, and then you can let them talk together.
It's scalable. Yeah,
and then it's scalable. So and that's how it is today. And then maybe 10 years from now, when memory is even cheaper, right? You don't only need maybe 10 computers connected, and it could actually have the power needed in memory storage to actually run this.
Right.
Okay.
Can I jump in
Yeah.
and suggest 7-minute break, because Doug, you are next.
Yeah.
So we can.
I mean, that was sort of a pre-question, but I had
Yeah.
one other question. If nobody else has another question, I can defer mine until my talk.
We need a small break.
Yeah.
So if you bring it in your lecture or after your lecture, we will have it more free.
Okay, so you're gonna take a break now. Okay, that's
Yeah.
fine.
We are
Yeah.
taking break now.
Yeah.
Okay. Thank you.
So yeah, thank you very much.
Congratulations. Yeah, good job.
So should we
Stop recording.
Yeah, and I have to find out where that is.
That's the one right at the end.
That more. That one.
Yeah.
Stop recording.
Yeah.
Yes.